The major thing in decision maths and this sort of maths that we're looking at the moment, it's a very powerful technique. It can be used in lots of different sorts of problems. What they're looking at here is this network. Okay, you haven't got to see all the numbers in that moment, but that is a directed network. And they're saying one problem could be they're all distances in miles. Find the shortest route from A to E. How would you go about doing that at the moment? Use one of those horrible things from last year. Yeah, which one? Dijkstra. Yeah, okay. And what are you trying to do in that problem? What sort of problem is it? It's a minimization problem. Okay. So that network there could be a minimization problem. That's fair enough. Okay, next. Each weight represents the weight limit of vehicles in tons that can travel on that section of road. What is the heaviest vehicle that can travel from A to E? Is that one we've done so far?
No.
It's not one we've done so far. What are you trying to look at? What are you trying to do there when you're looking for the route?
Find the smallest maximum.
Right, Jack, can you say that again?
Find the smallest maximum.
You're trying to find the smallest maximum. That's what Jack is saying. Is that correct? We're trying to find the heaviest vehicle that travels from A to E. Okay. What did you say, Jack? It was a
smallest maximum.
Smallest maximum. Or is it the maximum minimum? Right. Which one is it?
Smallest maximum.
Well, what's important? What's important is the lowest number on the route, isn't it?
Yeah.
So you're trying to make that lowest number as big as possible. Okay. So yeah, it's what's called a maxi-min problem, where you're trying to maximise the minimum value on the route. So that's a maxi-min problem, which you haven't come across yet. Number 3. The weights represent profits in thousands of pounds which can be made from carrying cargo en route from A to E. Find a maximum profit. So what are you trying to do there? Maximise, minimise, minimax, maximin? Maximising. Okay. 4. The weights represent the times in hours needed to walk between campsites. Find a route from A to E which keeps the longest stretch to a minimum.
You're minimising the maximum.
That's a mini-max problem. That is where you're trying to minimise the worst part of your journey, if you're a walker. That's a mini-max problem. Number 5. The weights represent activity durations in days. Find a critical path and the time necessary for completion of the entire project. What's that? Are you looking at minimising when you go critical path?
Just do most of the day.
Critical path, the homework you've just done. Are you looking? What are you looking for? It's not actually, no.
It's the longest time.
You're looking for the longest time. What take the longest time, which you cannot reduce. Okay. So networks can show all sorts of different scenarios. Some are minimising, some are maximising, some are mini-maxing, and some are maxi-minning. And so far you've seen different techniques for some of them. What we're going to do now is look at a general method called dynamic programming, which can do all of these things in a network. Richard Bellman, 1950, so again a modern area of maths. Okay, and we're going to see this as we go through. Copy this network down, please. First of all, can you copy this network down? Okay. Okay, nodes are called states. This is really important you get this in your head. Nodes are called states, and the directed arcs are called actions, and the weight on an arc is called the cost. So if you can actually copy that sentence down, the nodes are called states, The directed arcs are called actions, and the weight on an arc is called the cost. An action is what transforms a situation from one state to another. And if you think of the actions of the arcs, that makes sort of sense. An action is what transforms a situation from one state to another. And then this next bit is quite important. We'll try to highlight here that green bit, that's important. It says, if you look at the diagram you've already copied down, you can see that one state requires 4 actions before reaching the final state. 2 require 3 actions, 1 requires 2 actions. This state over here could require 1, 2, 3, 4 actions to get to the end. This state down here, what's the maximum number of actions this state? The maximum number of actions this state could take to get to the end.
3.
Yeah, 1, 2, 3. Okay. The final state requires no actions to get to the final state. The maximum number of actions to get from a state to the final state is called the stage variable. Starting there, finishing there, that sentence is vitally important, okay? Particularly that word maximum. If you could write that sentence down. The maximum number of actions to get from a state to the final state is called the stage variables. And it is the maximum. It's not... Because from that one at the beginning, you could go straight to the end in 2, but you look at the maximum number of actions that could get you there, and that's 4. And then on your original diagram, what I would like you to do is to label your original diagram with these stages. We just introduced the stage variable. Over here, if you just look up for a minute, this node here is stage 0. Coming to here, these activities are stage 1 activities, and you come backwards, and anything in this bit here, this is stage 4, because if you're over here, you could need up to 4 stages, up to 4 arrows effectively to get to the end, and you're always looking at the maximums. This node here, how many actions are needed to get to the end from here? 0. Now, for each of these nodes, I want you to write down 2 numbers. You may be able to fit them in your circles. If not, doesn't matter. Just sort of put a box there, something like that. And that takes 0 actions to get there. So you can put a 0 there. The top and the bottom one, what is the maximum number of actions needed to get to the end from this one up here? And what is the maximum number from this one down here? That's a 1 as well. The one in the middle, what is the maximum number of actions to get to the end from here? 2. So there's a 2 in the first box. These 2 back here, what is the maximum number of lines you need to transverse to get from here to the end? 3. And from the beginning one, 4. So we put in there those stages. Then the other thing we do, there's another box here, we put something else in. How many of these stage 0 boxes are there? 1. So we'll put a 1 in there, because we basically just number them. That's the first one of those. How many boxes are there that start with a 1? We put a 1 in the top one and a 2 in the second one. It's just literally a counting. That's the first one in that stage. That's the second one in this stage. In stage 2, there's only 1, so the second number there is a 1. In stage 3, there are 2. Top one gets labelled with a 1, second one gets labelled with a 2. And over here, in stage 4, there's only one of them. That one gets labelled with a 1. And those numbers are called state numbers, or state variables. So, what I would like you to do next is a sentence here. Okay. In addition to the stage variable, you can define a state variable for each state. And basically, it's a number of, you just number them as you go down the diagram top to bottom. So somewhere, can you sort of draw yourself a key? You've got now 2 numbers. This number here is a state variable, and that is just a number 1, 2, 3 down your diagram, and the first number here is your stage number. So you label each node with a stage and a state. The stage is the maximum number of lines to the end, maximum number of arcs to the end, and the stage is just 1, 2, 3, etc. for that stage. And we should then end up with the diagram that they've got here, bottom left. And label each node using what we've just done with its stages and states. If you draw the circles big enough, you can put both numbers in those circles. And that just makes it a little bit easier sometimes. And you just separate the numbers with a comma or something like that. So if you could draw that diagram, and for each one, first of all work out the stage number. And once you've worked out the stage numbers, then can you put the states in, which is at the top to bottom, numbering them inside each stage. End up with it labelled, as you can see there in that diagram. Okay. This chapter hinges on something known as Bellman's optimization principle. Okay, which is what you can see here on screen. Bellman was the person who we mentioned earlier on the beginning in the 1950s. To solve an optimization problem involving a sequence of decisions, you can work backwards. At each stage, you work out the best strategy from that point to the end, which is called the suboptimal strategy. And you do that and you keep working backwards through the problem until you get to the beginning. You do it in each bit of chunk. You just roll back all the time. You say, from point very near the end, what would be my best thing to do if I was here? And you just work backwards to the beginning. That's Bellman's optimization principle. So could you put a little heading, Bellman's optimization principle, and then if you could write that down. I don't know whether that's the box. Yes, that doesn't make any better, does it? Okay. So that's about as good as I can make it. So put a little heading, please. Bellman's optimization principle. And it is to solve an optimizing problem involving a sequence of decisions, you can work backwards. At each stage, you should work out the best strategy from that point, called the suboptimal strategy. First of all, the network you've actually got on the sheet that's come round. The question is, well, the problem here, suppose it to meet an increased demand, because you haven't got this writing on your sheet. Suppose it to meet an increased demand for electricity in a town, it's intended to increase the capacity of parts of the electricity grid on one route from the generator to the town. The costs in tens of thousands of pounds of bringing each part of the grid up to maximum capacity are shown. Basically, what we've got to do here is find the cheapest way of upgrading the grid. So you've got a sheet now which has that network on it. And what I would like you to do, first of all, is to label each node with the stage variable and the state variable. Remember, the stage variable, it says that it's a maximum number of arcs you travel along till you get to the final one. The state variable is just literally going 1, 2, 3 down each stage. Board, what we've got now is the correct labelling, if you just want to check yours. And then what I want you to think about now, there are 4 sorts of problems we can have. We looked at them earlier. A maximising problem, a minimising problem, a mini-max problem, or a maxi-min problem. What sort of problem is it in this question here? It's just a straightforward minimising problem in this problem, yeah. Okay. And once you have prepared your network like this with these stages and state labels, what we do then is we draw up a table. Now what I want you to do now is actually copy this sort of blank table down. This isn't going to be the one we're going to use for this question. This is like a template table which you can refer to later on. It's like a red box table if you want to think of it like that. Sort of, yes. I'll put the other lights on in the room. Don't know if this makes it any easier to read. I don't think it does. So, you have 5, well, you certainly have 4 columns. We ignore that last one for now, okay? We ignore the column where the pen is. A stage column, that stage column will only have like about 3 or 4 characters and doesn't need to be very wide. A state column, an action column, and a value column. I would make the value column usually a little bit wider. So you always have these 4 columns, stage, which are the first number in your labels, state, which is the second one, actions and values. And underneath the headings, underneath stage, it says here, start with stage 1. Under state it says, have a row per state for each stage. Under action it says, where can you go? And under value it says, what is the cost? And that is like a template table. And in a minute what I want you to do is we're going to draw a proper table out, the table for this network diagram, and you need to make sure that you have the network diagram and the table both visible at the same time. So don't stick the sheet in yet so you can see as we go. So when you do the table for this diagram, the first stage is stage 1. We needn't bother with stage 0 because stage 0 is always at the end. How many states do we have in stage 1?
2.
We have 2, yeah. I'll show you in a minute. I'll just wait for people to copy this down. Are there still people copying down from the board? Yep. Okay, just give me a shout when you're finished. And I suggest the next table you do, you start on a new page, because some of these tables are very long. And in the D2 exam, they had one last year that was just ridiculously long. But yeah, some of them do get quite deep. So I'll start this proper table we're doing on the new page. Can I move on? Just wait for John. Where are we? What is the cost? Oh, actually, don't worry about that column. Okay, don't worry about that column. Okay, if we can move on then. This is the proper table we're going to do for this network. It's going to be quite deep, but can you put this on a new page, the heading, stage, state, action and value. And in stage 1, there were 2 states. State 1 was node F, state 2 was node C. We write them in like this. So 1, 1 was F and 1, 2 was C. Between, also the end of a stage, you tend to draw a line all the way across. You don't usually write down its end of stage line, but that's what it is. So underneath stage 1, when you finish listing all the states, you usually put a horizontal line all the way across, and that is your end of stage line. Between states, you usually put a horizontal line across, but only from the right as far left as the state. You don't sort of underline, go below the stage number. And the actions are where you can go. So if you are at F, where can you go? Well, you can only go to D. So that is your action. And if you're at C, where can you go? Well, the only action you can go, the only place you can go is to D. So that is the starting out of this table. We're not going to do any calculations yet. We're just going to draw the table out to start with. Is everybody okay with that? Okay, when we come on to stage 2, how many states are there in stage 2? 1. And that's E, and I'll show you that one in the table in a minute. How many actions are there? How many places are there we could go from E?
3.
Yeah, we could go to F, we could go to D, or we could go to C. And that's shown on the table like this. Okay, there is your stage 2. There's only one state, it's labelled 21E. And from E, you can go to either F, D or C. It doesn't matter which order you write these in. Normally just write them in the order, top to bottom as you go down the table. There's only one state there, so the end of stage 2, with one state you just put a line all the way across. That's another end of stage line. Are we okay with that? So then we'll come on to stage 3. How many states are there in stage 3? 2. If we look at the first state, state 3-1, how many places could we go from G? 2, yes, so there'll be an F and an E action. Then you have your end of state line, not end of stage, end of state line. Then you list your 3-2 and where you can go from there, and then you have an end of stage line. Then finally you do the same thing for stage 4, which is your final stage that has 2 states, and each state has two possible actions, and then that is the table completed. In a minute we'll talk about what we do with the table. So once we've got the blank table set out, what we need to do then is start putting the values in. Now first of all, if you look at the top line we've got, this is saying at the moment we're at F, we're going to go to D. What is the value of that? If you look at going from F to D, we have a value of 8, so that will be the value that is put on there. And here, at the moment, our state is we are currently at C, and our action is we are moving to D, that is going up this arc here, and the value of that arc is 7. Now, every time you come to one of these lines, not the end of a stage line, but just the end of a state line, you actually look at all the options you've got. Now here there's only one option above that line, and there's only one option there, but in other places there'll be more than one option. And because this is a minimizing problem, we choose the minimum of the values we've just written down. So here the minimum of 8 and nothing else is 8. And whilst it sounds a bit silly at this point, you'll see later on as we go through how important this is. And here at the end of this state, in this stage, we've only got a value of 7, so that is the minimum. Now as we go on to our second stage, you'll see how that develops. So, stage 2, state E, that means we're currently at E, and here our action is going to F. So that is going from here up to here. The value of that is 3, plus getting from F to the end. And what you need to do now is find this letter a level up in the state column, which is here. And we know that once we are at F, we can get to the end in 8. So I add that 8 on. So that actually, if I'm at E, I know if I go to F, I can get to the end in 11. So my next action is going from E to D, and I know from getting to E to D, I can get there in 12, and that is the end. So there's nothing else to do with that one. Alternatively, I could go from E to C, which is down here, and I'm passing a value of 3 on that arc. And then C isn't the end, so what I need to do is find this letter C in the stage above, in the state column, which is here, and I know that when I get to C I can get to the end in 7. So what I need to do now is add that 7 on to give me a 10. That means if I'm at E and go to C, I can get from E to the end in 10. And now within this state I've got 3 different values, and I need to choose the minimum of these values. The minimum of 11, 12 and 10 is 10, so I'll arrow that one and label that one as the minimum. Now I'm moving on to stage 3, and in stage 3, just fold this over a minute. In stage 3, first of all I'm going from G to F. And if I look at this, from G to F is 5. And once I'm at F, to get to the end, I find F in the state column, and it has to be above here, so I'm going up to find F in the state column, and that's here. And I know then I can get to the end in 8. So I'll add that 8 on, and that will give me 13. My next action is G to E. G to E can be done in 3, and once I'm at E I need to find E in the column over to the left but higher up, which is here, and the minimum value from E I've already found is 10, so I'll add that on and I'll get 13. Now I'm at the end of this state, I need to choose the minimum of these values, and if it's a tie it doesn't matter which one you choose, I'll just choose the top one for now and label that the minimum one for that state. Continuing with the next state in this stage, B to E. B to E has a value of 6. I'll just do the first bit of these first of all, the diagram's here, and B to C has a value of 6. Now, if I'm taken to E, I look at my E up here, the minimum is 10, so that needs to be added on. Here this has taken me to C, so I go up to find a C in the state column, and the minimum there is 7. So I add that on. So here I get a 16 and I get a 13, and the minimum of those two is a 13. So I'll arrow that diagram. Then moving on to stage 4, where I'm going from H to G. H to G is 6, and H to E is 9. Then I look up my diagram. This has taken me to G, so I go up here to a G. The minimum is 13. That needs to be added on. If I've taken to E, I have to go all the way up here, and the minimum was 10, so I add that on. That will give me a 19 and a 19. I choose the minimum. It can be either, or I'll just choose the top one. That will be my minimum value. And the final state is going from A to E, which is 7, or A to B, which is 5. And to find the values that go with those, because here I've ended up at E, I need to find E in the left hand column, which is here. That minimum is 10, so I'll add that on to give me 17. And here I've ended up at B, I need to find B, which is here, and its minimum was 13, and I add that on. That gives me 18. So I now have the minimum of 17, and 18 is 17. And the next video will tell you what to do when you've completed this table, how to interpret it to find out your answer. Can we first of all circle that 17 down here, which is our best value in the highest stage state. That 17 depended on this 10. If you've got different colours or highlighting pens, it's useful to use that sort of thing here. So that 10 I put in a red rectangle. Where did that 10 come from? That 10 came from here. So I've now gone from A to E. And you need to write this down as you go. I went from A to E, and then from E, I went to C. So I'm tracking through now from E to C. That 10 depended on this 7. I'm going to put that 7 inside a triangle for a minute just to identify it. Where did that 7 come from? That 7 came from here. So before C, I came to D. So tracking through my network, that's a D. And that 7, that was in stage 1 at D. D was the end of the thing, so I finished. So the route I had through that network was A, E, C and D. And if you look back to your network diagram, A to E was a 7, E to C was a 3, C to D was a 7, and if you add those together, you get your cost of 17. So you found the minimum route through that network was A, E, C, D, and was 17. Now we could have found that minimum distance by using Dijkstra's method, but this is another method that you can use. It works on scenarios where Dijkstra's and others don't use. And remember, we did this one on a minimum here, but this would also work on a maximum or a minimax or a maxi-min as well. Afternoon, we've got a different problem to look at first of all. Same network, well, it's a network that has appeared in this book before, so don't worry about you've seen it before, I don't think you have. But we've got now the weight on the edges give the maximum altitude on that road in 1,000 feet above sea level. A traveller wishes to travel from S to T. They want to choose a route so as to minimise the maximum altitude above sea level along the route. They want to minimise their maximum. This is an example of a mini-max question. Okay, we haven't yet done a mini-max question. What I would like you to do first of all is just label each node, as you did this morning, with its stage and state number. So can you label each node, like you did this morning first of all, with its stage and state? You should have found that those are the labels you have. What I want you to do next from here is to draw out the table, the blank table. Don't do any of the values yet. Just start to do the table you will need. Remember, the table's headings will be stage, state, action and value. Don't fill in at the moment any of the values. Can you just get the stage, state and the actions done? Can you put the horizontal lines in between states and stages? And in a minute or two we'll just compare the tables you've got before we actually go through and work anything out, because the way of working it out for a minimax problem is different to the way we worked it out this morning. Should look like this. You've got 3 stages in your table. Sometimes you just got 1 state, sometimes you've got 2 states, down here you've got 3 states. What I want to go through now is starting to complete the table. So first of all, if you're at D, which is 1, 1 up here, which is where you start, the only option is to go to T. What is the value? 14. Yeah, that's it. It's the only thing there is to go there. And if you're going from E to T, from 1, 2, E to T, that is 2. The problem we are doing, we decided earlier, was a minimax problem. And because we are mini is the first bit of it, it is minimums that we are arrowing. So we're arrowing minimum still. If it's a minimax problem, you arrow the mini, you arrow the first bit there. If we look at 2, 1, which is up here, 2, 1 is going from A to D, which is 6. And then when we're at D, we've got to look up in a higher stage and find D over here. And we know from D, we've got 14. We're not adding those together. What do you think we're doing? Yeah, we are identifying the max of them. The max of the journey A to D and the max of what we had for D. So the max of 6 and 14 is 14. We're not trying to minimise across the whole thing. We're trying to minimise these maximums as we go through. So E, A to E is 10. And once we've got to E, we know our optimum value is 2. So we're then looking at the maximum of that 10 and that 2. And the maximum of 10 and 2 is 10. When we have finished that state, we now look to minimise. And what is the minimum of those 2? It's the 10. Okay? So we've minimised the maximums as we went through. So from 2, 2, which is here, going to D is 12. Going to E would be 6. And for D, we know the best thing for D in the state column is 14. So I'm maximising, looking there, the maximum of 12 and 14. And after E, up here, E in the previous column is a 2. And the maximum of 6 and 2 is 6. But I'm looking at overall to minimise, so the minimal one will be that 6. Can you have a go to see if you can finish that off the rest of the table? And can you see if you can backtrack through to work out what the path was? And in a minute we'll look at the completed table and we'll look at backtracking together. Fine, when you finish it off, we got down I think as far as that 6. There's a 15, a 10, a 6 and a 15. So in the final stage we arrowed a 6. That means we never have to go more than an altitude of 6,000 feet. And you can backtrack to see where it is. This is B, and B, that was from S to B. We used this 6. You think, where did that 6 come from? That 6 came from here, which was E. And that depended on that 2, and that 2 came from here, which involved T. I've done it here in colours so you can actually see the links. And if you write them down, those are the altitudes. The maximum is 6. The route is SEBT, and that is the route that will minimise the maximum altitude you have to have. Were you all okay with that one? Okay. Next one, can we find page 68 in the textbook? Page 68 in the textbook. And I'm going to go through that one there. Page 68, I mean, you can see it on the board. And what we've got here, if you look underneath the pen, we have a diagram. Each arc weight represents the weight limit on vehicles in tonnes that can travel on that section of road. We want to know what is the heaviest vehicle that can travel from A to E. So this time we're not trying to minimise overall, we're trying to maximise overall. And this is an example of a maxi-min problem. What I would like you to do actually is remove the book. No, not remove the book, sorry, but just see if you can do the labelling first of all, but don't look at the table in the book. Can you just do the labelling of the diagram with the stages and the states? Set out your table, and then last time, in the last question, we were mini-maxing. This time we're maxi-minning. So just do it at the same time. Each time, instead of writing down maximum of 2 numbers, you'll be doing minimum of 2 numbers, and you'll be arrowing the maximum in each state. So having had that one, from there, label up each node with its stage and state number, draw up the table, try not to look at the one in the book, try and do it on your own. But instead of doing max of 2 numbers, we will be doing minimum of 2 numbers, but we'll be arrowing the maximum in each stage. So it's the same sort of thing, but it's the first time with this one you're doing a maxi-min problem instead. So I'll leave the network there for you a minute. Table layout you should have for this question, a 4-stage problem, and the next clip will show you the completed values. So for the one you've just been looking at, completed tables here, you have your final value of 9. The route you can track back, which is what these arrows are doing here to a certain extent. We know it's A to C, then we can backtrack from there. It was E. ACE is the optimal route, and 9 is the weight of the lorry that can go through it. The next thing to look at is page 65. Page 65 is a critical path based on the network that they have at this point. The critical path is a maximisation problem. You're trying to find the longest, basically how long it will take if everything has to happen. So if you could try and do a maximisation on this network, they've actually already done the stage and state labelling here. If you're going to have a go at doing that one, it's just a straightforward maximise, not a mini-max or a maxi-min, a straightforward maximisation. That's how you do critical path. Okay? This final one, this critical path one, a straightforward maximising problem. So we have total down here, and we have the route. You can backtrack, sometimes using arrows, use a colour, sometimes helpful as well. And if you can do that maximising one, we've done a minimising one, a mini-max one, a maxi-min one, and a maximising one, and that is the end of the D2 chapter on dynamic programming.